So from this first part of the problem, remember we used conservation momentum to find that the velocity of the person in the gun immediately when the bullet exited was this term right here. That velocity was here. Since we're going to call this direction positive in this part of the problem, we'll get this, that by momentum, that this is that initial velocity now, as when the person and the gunner are hanging straight down, they have some initial velocity, and now the problem starts from here, and the question is how far do they swing? So once again, we have the choice, momentum or energy. Which way should I go? We'll start out with momentum this time, and we'll see why that will give us the answer. It's just going to be, it's going to take some more work with that than energy, and we'll see why energy is probably the smarter choice for this problem with the assumptions we're going to make. So we'll start out. Let's pick a system. You can pick person and the gun. You can person, gun, and earth. I'll just start out taking a choice, and we'll see why that would work, or we might have a different one we want to choose. Everything else is surroundings. We'll assume that started theta of 0, and this is my initial velocity of the person on the swing. We don't have to worry about the bullet anymore. The bullet's not part of our problem. It's just the person in the swing. And the final position is we're going to be at rest. So we come to we're going to have velocity. We're going to swing. We think we're going to be, intuition that tells you we're going to be slowing down. Eventually we're going to reach a 0 velocity at this point, and we'll probably swing down. We want to get to the point where it's 0 velocity. So at rest, at maximum angle. Again, I'm going to do momentum first, and we'll see why that would work. But from initial and final states, energy might be the better choice here. So free body diagram. So we're going to look at along this whole travel. He's going to be at some arc position, and let's just pick some position along that path. And so here's the person swinging around. We'll kind of pick him right here. Once again, we'll kind of think about coordinate system almost before we draw forces. So the rope now is in this some position, some intermediate theta, not at theta max, and we're gonna make assumption that the rope is not stretching. So kind of this length stays constant. That'll be one of our assumptions. So the stiffness of the rope is infinite. And so, once again, coordinate system, when you have rotational, you also want to think we're going to have something which is kind of perpendicular to that motion, going to the center rotation, perpendicular parallel, or radial and theta, or x and y, whatever you want to call it. That's kind of our thought process. This person's swinging around here, and he's at constant, we're going to assume constant radius, L. We're going to assume that these people are particles. We're going to assume mass of rope is 0, okay, and some other assumptions we'll talk about later. So, now pick any position here, draw a free body diagram. Let's draw all the forces. So we have a force of the rope. It's acting at that towards the center point right here. We have gravitational force, and we have a buoyancy force. As we talked about the other previous one, since the density of the air is so much less than the person with the gun, we'll assume that's the buoyancy force is approximately 0, so it leaves us really with just these two forces acting on it. We can define our coordinate system here and solve for the change in momentum with respect to time as the net force. So we'll assume mass is constant. So essentially gives us this term, the mass, and then change of velocity over time, which is acceleration, and my only force acting, using a little bit of trig right here, the only force acting in this parallel direction is this component vector of the gravitational force. And then in the radial direction, we're going to have, again, change of momentum is net forces. We'll get some acceleration here. The force is now acting. I have a component of the gravitational force. We'll call this the positive direction here, the cosine term of that, and then F rope. Okay, so now I have these two equations. The first equation will give us information about the acceleration of rotating here. The second rotation gives us about acceleration of going in and out. And so I can use these terms, and I can solve. Now, one thing about this, you can see that as I'm moving, this theta term is changing. So the magnitudes of my accelerations will be changing with time, and so I can take the integral of this and be solving over time steps and ultimately find what that final position is. But that would involve some iterations and some integrals to define what that is. So anything centered in rotating, yeah, I can find lots of information. I can at any moment in time, I can find instantaneously what's the accelerations. I can find parallel. I can find instantaneously that acceleration parallel. Instantaneously, I can find that acceleration perpendicular or normal or in the radial direction. At an instant of time, I can find the force in the rope. So that's really good for instance in time, what's happening. It's not very good from initial to final unless I integrate this over time. So this is very useful to find lots of information what's happening at any instant of time, but it's not so great at saying what's happening from one time period to the other unless accelerations are constant. And you can see in this case it's not. Accelerations are not constant, so it makes it more difficult to do this integration because these accelerations are functions of what theta I'm at. So let's consider using energy then instead. So in something that's rotating, and this might be very helpful because we have lots of problems that would happen, where something is rotating about a center point and it's at a fixed radial distance from it. In those kind of cases, you kind of think about like the rope force. So the rope force is always acting, we'll assume the rope force is always, we'll assume the rope mass is zero, so we'll assume the rope force is always acting from this particle to the center rotation. And then since we'll assume that this is not stretching at all, that is, as this thing is sweeping around, that the force and that the dr, I shouldn't really mean dr, probably a better word to say, d theta or whatever, the change in that position. Well, I guess dr. R is a little confusing because you might think radius but kind of the motion. So what the motion, the dx or the dy or what I want to call it, these are perpendicular. So we know that work done on anything is the dot product of the force and the change in the position. So which is the cosine related term, and when things are perpendicular to each other, then there is no net work done at it. So that helps us a lot to know that this rope is not doing any work on this particle at all. So, our force is acting. We have this buoyancy force we're ignoring. We have the rope force. We know that rope doesn't do any work. So the only force we have that's moving through a distance is gravity. And as we're swinging around, gravity is always pushing down, and the change in the position we're worrying about is we're only going to worry about the movement up and down. Okay, so the only work we're going to have done is by a conservative force, which is gravity, which means it doesn't matter where any start point, any end point. I just got to worry about the change in the distance which is in this parallel to that gravitational force. So we can solve for energy, final and initial, using kind of work equations, and considering gravitational as a gravitational. The person, gun, and the Earth are my system, surroundings, everything else. From energy, conservation of energy, we're going to say that the energy final of the system is the initial energy plus the work done in the system by the surroundings. And we just said the work done in the system and the surrounding is zero because we're going to consider the gravitational force to be an internal force, and rope force does no work on the system. So final energy, that's my energy of rest, my kinetic energy of and this time, since the person and the gun are moving together, I'm just going to consider them to be a lumped particle having the mass of the sum of the two. So rest energy, kinetic energy final, potential energy final, which is the only potential energy we're going to have is from the gravitational forces. Rest energy initial, kinetic energy initial, potential energy initial plus work, which we said is 0. We know that we're going to assume the rest energy are the same. In the final state, we're going to say comes up to stop, so we'll say there's no kinetic energy in the final. So we're left with the potential energy final, and bring that over to this side, minus the potential energy initial, which is the change in energy, which we know it's only gravitational, so we know that's mg delta h, where delta h is the change in the height. So that's from this position to there. That's my delta H. And that equals the initial kinetic energy. Initial kinetic energy, we're going to assume the velocity is much less than c. So that's 1/2 this combined mass times the velocity initially squared, which is, that's the velocity initial. So I can substitute for all those terms. I can, this is mgh. I know what that is. Okay. So I get this, the change in the height. So so just doing the algebra, I can get this equation right here for the change in the height is a term relative to the velocity initial squared over 2g. I know what the velocity initial squared, I can substitute for that is. I can do a little bit of trig. I know at time 0, or initial condition, I was at this length L. At the final position, my height relative to the center of the Earth is this right here is L cosine of theta. So delta H is L minus L cosine theta. I get that right here. I can do a little bit of trig, a little algebra, and I can then solve for theta. Okay, so is the arc cosine of this term L minus the velocity squared over 2g all over L. You might want to just do some dimensional check, is always good to do. So if I just look in this term, I know, this term should be, length term should have units of, for example, meters. So if I substitute in for the mass, velocities, and g being, so mass squared, kilogram squared, velocity, millimeters per second squared, g is meters per second squared, mass squared would be kilogram squared, cross everything out, and I end up with a length term, m, so meters. So I did the algebra right. So meters minus meters over meters is unitless. So this is my final answer for what angle that final thing would be. So this is the solution to the problem. And it can be derived at simply from using energy with these assumptions.